Hi, my name is Pramod of the CoinOp Collection Group, and today I'm going to show you all about schematics. You hear a lot of people talk about FPGA, and having the schematic is great. Decapping chips is great, you hear a lot of talk about it. And the fact of the matter is that the schematic and or the decapped version of the chip, or rather someone goes through and applies acid or some sort of wash to the chip to reveal its internal silicon, and goes through with the microscope and observes it and models it by hand in HDL and all that stuff. You hear a lot of talk about it. You hear a lot of talk about accuracy, and it has to be purist and all that stuff. But what does it actually mean to have these pieces of information? The fact of the matter is that these are two sources of information for making a core. We have the schematic. The schematic definitely helps. Decaps definitely help to a greater or lesser extent, depending on what it is. And these are just two sources of information that we use to make a core. They're not the only primary sources of information that we use, because if we were to just use those pieces of information to make a core, we wouldn't really get very far, because there's a lot of other information that you need that entails reverse engineering the program that runs on the board, reverse engineering the board itself. Just decapping the chips and modeling them doesn't really give you everything, right? There are certain parts that you have to research into and reverse engineer, and people have done that over time. Right, people have done that in the past. They've done it, and the results of that appear in MAME or other emulators, software emulators out there. People have done the heavy lifting of reverse engineering things, because back in the day, it wasn't really common to decap something. Right now, and nowadays, I mean, it's still prohibitively expensive, but nowadays you have a lot of people who decap chips and scan them. They have microscopes and they can go through and model everything. And so nowadays it's more common, but back then that really wasn't a common thing to do. Same thing with schematics. I mean, certainly schematics existed back then. People would take a look at them, but they weren't. I mean, they didn't have really the tools to, really take a look into the traces and, desolder them and, apply all these sorts of different techniques to, scan them and, model them and all that stuff. Those tools are more prevalent today. So in this video, I'm going to show you what the schematic actually does for you. What is the purpose of it? What information can we get from it? And how you take that and actually model an FPGA module based on it. So I'll be taking you through a little bit of that. I won't do the whole module. I'll do a lot of it, but I won't do the whole thing here for lack of time. To start, fortunately for this project, and you can see on your screen, I am looking at the Smash TV audio board, okay, which I do have in my house here, and I've taken a picture of it this morning. I've taken it and it appears right here. I've just taken a top view picture of it. Normally, I would take multiple pictures and then merge them in, and so I can see the undersides. Just so I have all the readily available information in case there's any doubt. But for this audio board, it's not very complicated, so I've just taken a top view picture just to because I already have a detailed schematic here in the manual that I have, so there's not really a need to take a full-on deep picture of this board. Okay, so I have the real picture here, and primarily the reason why I have the real picture here, that I've taken a real picture here as opposed to just using the schematic, is because you can see some of the text is blurry here where it says perhaps a part number, or like, for example, this is a part number, right? This is a 6809 chip, right? And I know that already because I've already looked at the picture right here. But yeah, we're going to go through all that. But primarily for legibility purposes, I've taken the picture, and also to take a look at the detailed part number, because when you get down to RAM chips, for example, you want to take a look at the actual part number and search that up and see how much it was, what type of RAM it is, what latency it is. Like, just take a look at the data sheet and see, what sort of latency it has, how fast it's expected to operate. Because RAM, I mean, for these types of boards are really high end, I would say. They generally use a lot of SRAM, and the same is true here. The U5, I think, is the RAM chip. It is SRAM for sure. Yeah, and a lot of the memory operates really fast. The ROMs operate really fast. These are the ROMs. And so you want to take a look at the part number, and I'll show you how to do all that stuff when you're looking at a schematic, and what information to look for. Okay, so let's go ahead and dive deep into this. When I take a look at a schematic, um, generally speaking, I ignore a lot of the fluff. So this stuff right here, for example, at the very bottom of the screen, like resistors, all this analog stuff, I generally ignore. And I usually just focus on the major parts of it. Oh, what are the major parts of it? Okay, well, the major parts are in this schematic are the U chips. Okay, the U chips are the major components of this schematic of this board. Okay, and you can see there's different markings, right? There's U11 here. There's U12. There's U3, U5, U4, 19 and 20, U8, and then let's see, what else do you have here? Yeah, I think this is U16 over here. It's hard to read, but I think that's U16. And I think that's about it. Yeah, and there's a U1, of course. Okay, so where do you start? So you start by ignoring all this other fluff, right? You don't need to know about resistors. You don't need to know about AND gates, OR gates. They may play a role later on, when you get down to the detail of it. But the first thing you want to do when you take a look at a schematic is take a look very high level into and understand the architecture of what you're looking at. Now, generally, I do this at the beginning of the core building process, right? So when I start to build a core, I take a look at all the boards involved. If the arcade board has like 4 PCBs connected all in parallel, like NARC, I would go ahead and physically inspect the PCB. I'll take a look at some of the part numbers there. I'll take a look at the schematics. So for that game, I also have schematics. Fortunately enough, for a lot of the Midway, I pretty much all the Midway stuff that I've been working on, everything has schematics already published, right? Everything's already out there. All the part numbers are there, and I can read into it and see what the part numbers are. So in case there's any doubt about the latency or how fast it operates or how much data it can store, and what the specification of it is, that information is already available. So I haven't had a need to actually pull out the board a lot of the time. And so that's why I've been lucky with this. It's all been in manuals and technical digests and pictures online with schematics and manuals and all that stuff. So a lot of this stuff is already like kind of there. But the problem is there's a lot of detail to sort through, so it takes a long time to do it. So I go through step by step and I try to confirm all the information. Okay, so now that you know that, you generally ignore all the analog stuff, right? The AND gates, OR gates, the resistors, capacitors, like capacitors right here, like you ignore all that stuff, and for the moment, ignore the pins out to the bus, to other buses. So, like for example, this J4 here. This J4 is a CPU data interface, right? So that's a bus going out, and this is actually in a ribbon cable that attaches to the primary board. Okay, so we're going to ignore that for the moment, because we are not concerned ourselves with other boards right now at the moment. We're just focused on modeling this board. Okay, so let's start at the top left-hand corner. So we're talking about a chip called U8. What is U8? Okay, U8 is what? Let's take a look at this. Where is U8 found? So here is U8, right here. It's U8. And that is the 6809 processor, right? So right off the bat, you know that this board has a 6809 processor. And so what I'd start to do in my code is I'd start a new module. So I'm calling this YUnit sound, right? I have a starter clock and reset signal here, and I will just add that here. So I'll add a comment that says 6809, just as a note to add that IP later. This IP exists already, so I don't need to worry about that. In the beginning of the core building process, I've already taken an inventory of all the IP that is non-existing and the things that are existing. So I know about the 6809 already. This is the first time I'm actually like building the sound module for the Y unit. I've done a modeling of the Z unit, at the start of this project, but I haven't had time to debug it. So now I'm going to actually do the Y unit sound. And actually, there's several different variants of these soundboards. So we're going to take a look probably in another video on how we adapt the core to several different types of audio boards and or variants of the module to make a multi-game core work, right? And dispatch between the several variants for the different games that it can play. Okay, so we got the 6809 in there. Okay, what else is there? So we have a U4, a U19, and a U20, right? They're all in series, right? So they're all connected here. So the address, as you can see, like you see, this is a bus line, right? And all the addresses you see are really connected here. See, look, A0, the U20, A0 to A14 on this side goes all the way on the same bus, and it connects to U19 and U4. So that tells me these are probably ROMs. These are bank switched ROMs that go on the same bus, and you can select between them. And is that right? It is indeed right. So you have a U4 here, a U19, and a U20 right here. So these are all ROMs. Now for ROMs, we're not going to model that in the sound module in the FPGA core, because the ROM is actually not something that appears in the audio module in the FPGA core, because the ROMs come from SDRAM, right? We load the ROMs to the SDRAM at the start of the core, right? So they come from somewhere else. So all we have to do is add signals that go into this module to get them, and then we have to add request lines out to request the SDRAM or whatever controller is in place to get us data for the sound, right? And we don't know yet if this is sound, or if we don't know if these are sound samples, or if these are the program for the 6809 or not. But my guess is, by taking a look at this, is that this is probably an audio program. This U4, this U19, and this U20 are probably sound and speech samples. That's what I think, but we'll see if we're proven wrong later. Okay, so in my Verilog code, what I'm going to do is I am going to, okay, so I'll take note of the bus width right now. So what I need is a 8-bit input for ROM, right? So this is D0 to D7, right? So it's 8 bits width going out, right? In this bus line, and the addressing goes up to 15, right? Because it's A0 to A14 on all 3 chips, right? So what I'm going to do in my Verilog code is I'm going to do input let's see what an appropriate name is. Maybe sound prog D out, and have that be 70. Output sound prog D. I'm sorry, sound prog CS, but let's not have that be 70. Let's just do it that way. And then we're going to have an output for the address. So output, and it's 14.0, right? Let's make a check here. Yeah, 14.0. Sound prog adder right there. All right. So those are the three lines that we need. So we have a request signal, the CS. We have the address that we're requesting. We have the data that comes in. And finally, since it's from SDRAM, we need an OK signal. Beautiful. Okay. So we got our 4 lines. And usually what I do is I separate the lines by comment and I say audio ROMs. Okay. All right. All right. So let's, whoops. Yep. All right. That's fine. Okay. Now, let's go to the next part. So we have that. We have the ROMs going. The 6809 processor will leave there for the moment. Let's see what U5 is. So U5 is what? U5 is an MK6116LN-15. So I would go on Google and I would search for MK6116 LN-15. LN-15. Okay, and I'll take a look at the just any old link that comes up. So it's an SRAM chip, right? So it's an SRAM chip, 16K bits. We got 8 bits per word, right? We got 24 pins total. Okay, and so this is an SRAM chip, right? And judging by the schematic, it looks like it's also 8 bits in, and also it looks like it's 10. I'm sorry, 11. It looks like the address width is 11 here for this SRAM. Or is that a signal too? I don't know. I can't see that honestly in the schematic. I can't tell if that's an A11 or not. I think it is an A11. This might be an A11. So it's A11 to A0. So it's 12. It's 12 bits. It's 12 bits that are out, and it's 24 pins total. Well, we can take a look at the data sheet, but let me see. That's more. That's the same website, right? It's like more of the same nonsense. There's usually a link that comes up that's better from like Mauser or something, but I guess. Let me see here. Oh, this is a different chip, actually. Okay. All right. All right. So let's not worry about it right now. That's fine. Let's not worry about that right now. Let's just say it's, yeah, I think that's an A11. I think that's an A11 because look, it's just 2321 is A11, so it's probably a bank switch or something. Because it goes to the same bus actually. So this is a common data bus. It looks like that's shared by RAM and ROM. So that's something that we might need to pay attention to in the, well, no, that is something that we need to pay attention to in the Verilog code, because if you see here, this bus line goes all the way to the CPU, right? This CPU, right, has a direct line, as you can see, like the data lines are connected all to this bus. This is all a common bus for the audio chip, right? So all the audio board. So we have the RAM and the ROM sharing the same bus. So in order to get these data lines to the CPU, we'll have to add an address bus switcher somewhere. We'll plan for that, but basically that's what that means. When we're looking at the schematic. We're going to add some SRAM here. JT frame dual RAM. And we'll take a look. I'll just show you what the syntax for that is. So JT frame dual RAM, right? Which is right here, right? Now, this is what the signals look like. So right here, right? And so we said the address width was 12, right? The address width, yeah, I really think that's an A11 right here. That's what I see anyway. So yeah, I think the address width is going to be 12. And so AW12, DW is 8, sound RAM. Okay. All right. Okay. And we'll see. I don't know quite yet. I haven't decided what these data signals are just yet. I'm just creating a placeholder for it. Okay. And as you can see, those are the exact same ones that we had here. Okay. All right. And the clock will be our master clock. This is our master clock, by the way. We haven't created clocks or clock enables yet for the other stuff, because if you have multiple components on a board, right? Usually the philosophy of JT Frame is your entire system is driven off of one master clock, and then you use multiple clock enables for the different components, right? So for example, if your CPU runs at 48 megahertz, then and your master clock is 96, you would divide that signal by 2 and create a clock enable that runs at that would effectively make it operate at 48, right? In this case, I think we're dealing with much lower clocks, like a 3 point something, probably, or a 2 point something. It'll probably be 3 or 2 megahertz, something like that. So we'll see what happens as we go along here. So we got that going. And I'll note more specifications here, but just for the sake of brevity here, I'll just type in SRAM there. Okay, what else is there? Okay, so there's a U3. What is U3? What is that? Let's see what that is. Okay, so U3 is here. So U3, it looks like, is the YM2151, which we're all very familiar with. I think it's pretty common. I mean, I've used it in the Rising cores as well. I've used it in other areas too. Now there's two 2151 modules out there. I think one is from Jose. So that's the one I use because that's the one I'm just most familiar with. It's done pretty well. And I think it's and that's what I'm going to probably use here. There's a newer one though, by Rocky, who's another developer. And apparently it's pretty good. I don't know. I have not used it. I've heard it's more accurate though. But I have not used it, so I don't know how to use that IP. I could import that. I could swap that in for this, but I'm just not familiar with it enough at this point to do that. So what I'll do is I'll actually copy this bit from my previous implementation here of the sound. So I'll just take like I'm taking boilerplates basically at this point, right? JT51, here we go. I'll just paste that in here just for the moment. Okay. Clear all signals. Oh, that didn't do a good job. What's going on? Make all the connections empty. There we go. What happened? Where did it go? Oh, come on now. Make all the module connections empty. Oh, that's weird. What happened? Okay. All right. It did it, but I think because my resolution is low, I didn't see the box, or the box like disappeared prematurely. So I'll just like zero this out. It's fine. Whatever. Just zero this out and be done with it. Okay. That's fine enough for now. Okay, so we have a JT51 there. So this is a YM2151. Okay, so we got that placeholder in there. Beautiful. All right, let's go to the next one. So the next one is a U1. What is U1? Let's see what that is about. U1. It's a big chip. It looks like a big chip on the paper, but I'm not sure if that's true or not. U1. Oh, here. It's a YM3012, it looks like. Oh, it's not so big. I don't know what happened here. Oh, it's just like, oh, there's a few signals. It's just expanded for like space purposes. Okay, so this is a YM3012. What is that? Let's see what that is. I'm not familiar with that. Um, what is this supposed to be? Oh, it's a DAC. It looks like it's a DAC. I think it's a DAC. Let me see here. Yeah, it's a DAC. Okay. Yeah. So for DACs, I generally don't worry too much about them. And I don't really model them because I don't know why this is, but like I think that the framework for the FPGA already includes a digital audio converter from analog to digital. I think that's already inherently built in. At least I've never had to model a DAC for a core before. I mean, it remains to be seen for this whether that is going to play a role or not. But for now, I'm not going to model it. I'm going to make note of it, but I'm not going to model it for the moment. 3012 DAC. I'll just add question marks just to emphasize that I don't know what the hell that is yet. Okay. All right. So we got the U. That was U1. Okay. So we finished with the first row. Okay. Now let's go to the second row here. And we have a U14 and a U16. What is U14? Let's see what that's about. U14. Where is that? So the U14, I don't think we're going to need to worry about that. It looks like a logical component. T7 for LS13. T7 for LS13. LS13. What is that about? Okay. 7.4 LS. Oh, okay, I got it. Never mind. It's just a variant of the 7.4 series chips. So those are, yeah, these are logical chips. That's fine. I'll just ignore that. That's fine. Okay, and the U16 is what? Let's see what the U16 is. Same. U16. Yep. It's just another type of the same kind of chip. It's a logical chip, I think. All right, so we ignore those. Okay, so let's talk about U12 now. What is U12? U12 is what? U12 is the 68B21P, right? And that is probably the parallel interface adapter chip. 6821. 68B21P. B21P. Yeah, so it's a peripheral interface adapter. So that's going to be the thing that you see this CPU data interface out. That's going to be the thing that interfaces. That's going to be responsible for interfacing over a parallel interface to our main board. Okay, so we do have a IP for that, and I did note that in my initial assessment of the board. So I'm going to add that right over here. 6821 PIA. And the 6821 PIA is going to be in components, and here's your PIA 6821. So these are the ports. I don't know how this is going to turn out just yet, but I'll figure it out. PIA 6821 U6821 PIA. Okay, and we'll just keep that here for the moment and just see what comes later on. I'll leave the port definitions there too because I don't know yet how this is going to work with the stuff in this module. I will connect it up when I have the rest of the information. Like you see all these stuff, like I don't know where all this stuff is going to go. But U12 goes hand in hand with U11. So what is U11? U11 is, drumroll please, 1408P8. MC 1408P8. Let's see what that's about. I think it's a DAC. Yeah, it's a DAC. It's another DAC on the board. So let's make note of that. Connect to 1408 DAC. Okay. All right. Next one. So we got that going, and then you have, so that's U11, right? And then in the middle here you have a U6. What is U6? U6 is the next chip next to it. So this is the 55564. The 55564 is actually a CVSD, and I know that because NARC has the same one. So the CVSD, like I was explaining in the other video, was an older technology that did speech playback and samples. So like nowadays you have like you have the newer Oki chips, right? And they do speech and voice and all that stuff, multi-channel speech and voice. CVSD is an older technology. I forget what it stands for. I think it's continuous variable slope delta or something like that, right? And basically that is an older technology that allows voice modulation and speech samples to be played in your game or whatever you're building. So it's an older technology, and I guess this board has it. I think some of the newer variants of the soundboard don't use that. They use the newer one. They use the newer Oki chips for those because those are better. Okay, so this chip is U6, and in U6 I'm going to whoops. All right, so U6 is going to be that that other one. So I'm just going to copy it here. Just the definition. And the module is actually right here. So there's only 5 signals for this. And basically, I will just figure out what that needs to be in a minute. Or when I do the stuff, I'll just figure that out what that needs to be. Okay. Anything else we see? I think that may be about it. Oh, there's a U7, but I think that's a logical chip. That's probably something that we don't have to pay attention to. U7. Oh yeah, okay. Yeah, I think that's the same logical chip. Okay, that's down there. And I think that's about it. I think that covers the entirety of the IP on the I mean, at least on this board. Anyway, we don't know how the stuff will connect just yet. But what we do know so far is that everything will share a common bus in terms of getting its data to and from the CPU. And actually, this U12, this parallel interface thing, also has a line to the bus too. So we may need to address that too as well. So we'll pay attention to that, when the time comes. All right. So now that we have all of our IP in this module, right? So to recap, we have SRAM. We have the YM2151. We have the parallel interface adapter. We may have a DAC or two that we need to worry about. And then we have the CVSD that we have, which provides voice samples. There's a couple more things you need in sound, which I'll show you from this module that I've created here. Okay. Oh, wait. One more thing I forgot to add was the 6809 processor. So I'll just add a 6809 from here. because that is that's also here. I'm gonna try this one more time, just for the sake of it. Um, make all the modulations blank. What just happened? All right. I think it's because my screen is like, come on, don't. Ah, oh, yeah, it's because my screen is cut off for this, to connect to OBS. All right, no worries. Whatever. Um, reset clock. Okay, so this one has a clock enabled that we have to think about, so we'll figure that out later. I'll just blank out all the rest of these signals. Start fresh. Okay, got bus sharing in there too. Okay. All right. So that is that. Okay, so we got that going, and then basically, let's not do the RAM in here because, yeah, let's not do the RAM in here because let's before we do that, let's just like figure out. I just want to figure out probably like how the mechanics of this RAM works, and then because this RAM might actually be shared amongst like other things. That's why I don't want to really do it here right now. Okay, so we got that going. We got this. We got the 6809. We got the YM2151. There's only one of them on the board. And we got the PIA 6821, and we have the CVSD voice modulator thing or speech thing that we have here. Yeah, so that is a good starting point for us at this point. So that's generally what I would do when I'm going through a schematic is I would just look at those higher level components. And the next step that I would do, right? So now that I have a base template for my module in FPGA, what I would normally do is I would actually go through these connections and see. So like you see this bus, this is probably the first thing I'm going to do is I'm going to take a look and see like how all these things, like what is the addressing for this? Like how are these devices addressed? Right? Because if you share a common bus, then that probably means that there are different address ranges, right, for different devices to be addressed on the bus, right? And obviously there is a mux or something that dispatches the data outputs of any one of these components to the CPU and or other devices, right? So that's something that I would probably take a look at first. And in order to do this, I would probably take a look at MAME because this schematic is not detailed enough to say what the addressing is for any of these components. It just says that the addressing is all connected. So you can't really tell off the bat, what the addressing actually is. What are the address ranges on the bus, or how does the bus operate? That's not something that would normally be communicated in a schematic, but it is certainly in an emulator, right? So I would look to a software emulator to see how the bus operates and what sort of data it shares to and when to the different devices and how those mechanics work. So I would probably like load up an emulator and I would debug it and I would see how this bus actually operates and program that in to Verilog. And then after I do that, I would focus on the outbound connections from the module. So at the moment, we've only concerned ourselves with just basically the clocks and also the program because we know for sure that's going to come from outside of our module. We know for sure. Okay. One more thing that we have to probably do is this PIA thing. This is probably one or more of these signals is going to have to be, I've never actually used that before, but like one or more of these signals are going to go outbound from this module to the CPU, most certainly, right? And so we'll have to figure out how the mechanics of that work, right? And that's That's another area where I would look to an emulator. Now, you see all this stuff that we talked about before, like how these different chips share a bus and all that stuff that you model. And maybe I think there's other signals too. Maybe potentially ones that drive interrupts or signal the CPU that, oh, audio processing is done. There are maybe signals like that. Those kind of things are not really in an emulator, right? So this is like really low level information, and so these informations are not normally in an emulator because they don't really need to be done all the time, right? I mean, interrupts obviously need to be done, but what I'm saying is like pin connections back and forth between the different chips and all that stuff is not something that's modeled in an emulator, in a software emulator. So we have to take account into that in when we start to do the FPGA core, because all of it is really hardware modeling, right? We're doing hardware modeling, so those are things that we need to take into account, when we do that sort of thing, in Verilog. So okay, so that's it for this video. I don't want to go too much more at the moment, because I want to keep the scope of this video small to digest. But in the next video, what I'll do is I will go ahead and program some of these, like program in this interface, and then I'll review with you guys what I actually did and what decisions I made when I was writing the Verilog code and how it all turned out, how to model all this stuff. Okay, so I'll see you next time.